next couple of videos, we're going to talk about different types of chemical reactions. The first of those is going to be precipitation reactions, and this is closely related to the previous video on solubility and solubility rules. So precipitation reactions occur when dissolved substances react to form one or more insoluble products. And so the insoluble products that are formed, because they're not soluble in that particular solvent, they'll fall out of solution as a solid. And we call those solid products precipitates. And so what typically happens in a precipitation reaction is we have two aqueous solutions. And remember that when we have ionic compounds that are dissolved in water, they dissociate into their ions. So when I have a solution of sodium chloride, I really have sodium ions and chloride ions. And when I have a solution of silver nitrate, I have silver ions and nitrate ions. And so when I add these two solutions together, I get a mixture of sodium and chloride and silver and nitrate ions. If any of the pairs of ions can form an insoluble product, they will, and it will form that precipitate. So when we look at the solubility rules, we really only have to concern ourselves with the positive ions combining with the negative ions. And because we know because sodium chloride and silver nitrate are both soluble, right? The sodium chloride and the silver nitrate aren't going to be insoluble products, but if I swap the sodium and then combine that with the nitrate and the silver with the chloride, those are our other possible products. And if you go to look at the solubility rules, chloride compounds are generally soluble, but silver is one of the exceptions. And so when I mix these two solutions and the silver and the chloride ions are now allowed to interact, they will form an insoluble precipitate that will fall out of the solution as a solid. And this is just another picture showing the same thing, but now we have a better picture of what you would actually see it look like in the laboratory. Here we have the two soluble compounds, potassium iodide and lead-2 nitrate. And so the potassium iodide really has iodide ions and potassium ions floating around, and the lead-2 nitrate really has lead ions and nitrate ions floating around. When I mix these two together and the lead and the iodide ions see each other, because lead-2 iodide is insoluble, they will fall out and form this yellow precipitate, this yellow solid that will settle to the bottom, and then the potassium and the nitrate ions, because potassium nitrate is soluble, right, those ions remain floating around in the solution. So precipitation reactions are examples of what are called double displacement reactions. Because if we think about the example that we had in the first slide, what happens in these double displacement reactions is we're just swapping the cations and anions between the two compounds. In this case, the Na plus was paired with the Cl minus, and in this case, the Ag plus was paired with the NO3 minus, and so we're just swapping the cations and anions of each compound to form the new products. And so we get silver chloride and sodium nitrate. Of course, we always write the positive ion first when we write the products. All right, so we want to be able to predict the products of precipitation reactions. And so to do that, we would follow these steps. I'm going to go through these kind of quickly. What you may want to do is pause this and write them down. But I think it'll make the most sense is when we apply these rules to some specific examples. So what we want to do is first determine what ions are present in each aqueous reactant. Then we want to determine the products. And to do that involves two steps. So first, we're going to exchange the ions. So the cation from one compound will combine with the anion of the other compound. And the same thing for the other cation and anion. And then it's really important to determine the formulas of the products. Don't rely on the subscripts of the reactants. It's all about the charges, right? So forget about what the formulas of the reactants are. All you need to do to determine the formulas of the products is use the charges, like we would for determining the formula of any ionic compound. Then the next step is to use our solubility rules, which will be provided to determine whether the products are aqueous or solid. Now, one important thing to keep in mind, if both products are soluble, if they're both aqueous, then all we have at the end of this mixing is the ions floating around, and they're not going to react with each other. So unless we have a solid product, the products of the reaction would actually be no reaction. And then the final step, as long as there is a reaction, if there's no reaction, we're done. If there is a reaction and one or more of the products are solids, are insoluble, then we would balance the equation. Right, so let's do some examples of this. Right, so I want to predict the products and write the balanced chemical equation when aqueous solutions of lithium carbonate and calcium bromide are mixed. Right, so it continues to be very important to know the formulas of the polyatomic ions and to be able to predict charges based on an element's position in the periodic table. So lithium is Li plus, carbonate is CO3 2 minus, so the formula of lithium carbonate would be Li2CO3, and that's aqueous, because they told us it was aqueous, or we could go to the solubility rules and know that. And then the other compound is calcium bromide. Calcium is an alkaline earth metal, so it's 2 plus. Bromine is a halogen, it's -1. So we have CaBr2. It's aqueous because they told us, or the solubility rules would tell us that. Alright, so when we're determining the products, the first thing we need to do is determine what ions were present. Right, so in the way that this problem was worded, we've really already done that. Right, I know what the ions and their charges are in each of these compounds. If they started us with this, right, instead of giving it to us in with the names, if they just gave us the formulas, the first thing you'd want to do is write the ions above each compound. And don't worry about the fact that there's 2 lithiums. All I care about is the fact that it's Li and its charge. So the charges are important. Right, and then to predict the products, we're going to swap the ions, the cations and anions of each compound. Right, and I like to say I'm swapping the innies and the outies. Right, so the lithium and the bromine are on the outside, they get combined, and the calcium and the carbonate are on the inside, they get combined. So the compound formed between lithium and bromide ions, well, lithium is +1, bromine is -1, and so that would be LiBr. And then calcium carbonate, because they're both plus, or calcium's +2 and carbonate is -2, it's going to be CaCO3. Now remember, I didn't take into account the fact that I had 2's for the lithium and the bromine here at all. That doesn't matter. I'll take into account the fact that it's not balanced in the last step. The last thing I'll do is balance it, right? To determine the formulas of the compounds, all we want to use are the charges. Alright, the next thing we would do is go to the solubility rules. I didn't put solubility rules here, but if you want to pause and go look at them, you can. But according to our solubility rules, lithium compounds containing lithium ions are always soluble. There are no exceptions, so lithium bromide is going to be aqueous. Compounds containing carbonate are generally insoluble. Calcium is not an exception, so that's going to be a solid. And so I've got the states, because one of them is a solid, I don't have no reaction. And so the last thing I need to do is balance this. So the calcium and the carbonate look good, but in order to balance the lithium and the bromide, I need to put a 2 in front of the lithium bromide. And now it looks like it's balanced. Alright, so one more example. We want to predict the products and write the balanced chemical equation when aqueous solutions of aluminum sulfate and barium hydroxide are mixed. I wanted to show you how would I approach the problem if I was starting from the formulas and not the names. So I've gone ahead and written out the formulas, and so we can proceed how I would go from here. Right, so if I want to predict the products, the first thing I need to know is the ions and their charges. And I usually write those above the reagents. So let me use a different color here. So aluminum ions I know are +3. Sulfate I know are -2. And notice, right, I don't care about how many aluminums and sulfates there are. I just care about what their charges are. And then do the same thing here. So barium I know is +2. hydroxides are -1. And so now to predict the products, right, I'll take the ones from the outside. And so aluminum and hydroxide, because aluminum is +3, hydroxide is -1. That should be AlOH3. Right, the ones on the inside, barium and sulfate, so +2 and -2, so BaSO4. Alright, so now if we go to our solubility rules, so aluminum is not in there, but hydroxide is. Hydroxide compounds are generally insoluble. Aluminum is not one of the exceptions, so I would expect that to be solid. I go to barium sulfate. Barium's not on the list, but sulfate is. Sulfate compounds are generally soluble, but barium is one of the exceptions, so that should also be a solid. Right, so I'll get a reaction as long as one of them are solid. I'll certainly get a reaction if both of them are. And so then to balance this, let's see, I want to balance the hydroxides first. And so I want to do a 2 and a 3. And then I think if I do a 3 in front of the barium sulfate, then the reaction will be balanced.